waterborne disease. And this week we're going to the next chapter. We'll be talking about the water use and waste water generation. So I'm now on the slide of the chapter 3. Hopefully your screen is showing the first page of my presentations, the chapter 3, water use and wastewater generations. So water use and wastewater generation both have a very close link with each other because whatever the amount of the water we used, at least 60–70% will become the wastewater. There may be a loss due to some activities. Sometimes we're watching our car, sometimes we're watering the vegetations of plants. So that is the amount of water we lost. But anyway, say like 60–70% in general, it becomes a wastewater. Let us begin with the water use. Water use trend. Water use, as we know that the communities we are using water for several purposes. We used in our house, which is called the domestic use, at the hotel or even at the factory. But for the toilets, we also consider the water use in the toilets wherever it's located. We consider this water as the domestic wastewater, domestic water or domestic used, because this part is used for the human activities. Okay, that is not for the industrial activity or the manufacturing process. So anyway, we consider all the water used according to the human activity as the domestic water used. But anyway, for the domestic used, the amount of water that the people consumes may be vary depending on various factors. The economic levels for the rich people or the high income people, they tend to use more water. For the lower incomes people, they tend to use less a quantity of water in their daily life. Just compare the toilet facilities they have in their house. So you see something different. For the low income people, they may be happy to use the pour flush latrine. But for the high income people, they are likely to use the flush wall or the flush tank water closets. So for the flush wall and all the flush tank water closets, so one flush consumes at least 6 liters. So just imagine. So for the manually flush toilets, just 2 bowls are maybe enough. So 2 bowls is equivalent to like 2 liters. But for the flush wall or the flush tank water closets, so it may take at least 6 to 8 liters per one flush. So for one time using the toilets, the people may at least flush 2 times. So in that case, almost 20 liters is gone for the just one time using the toilets. So the domestic used may be vary depending on many factors. Economic level may be one of the most concerned factors. Commercial and industrial Of course, some communities or some cities, they may have the industrial activities, and they may have the commercial areas, and this area they generally consumes lots of water. But in some cities, they may not have the industrial activities in their area. So in that case, this part may not be taken into account. But anyway, for the industrial water used nationwide is generally about 200% of the municipal demand. Commercial consumption for the cities, as with the population as large as 25,000 persons, the consumption may be around 50% of the total. Anyway, this portion may be varied depending on the city, depending on the types of the industrial activities, because industrial activities, each manufacturing process requires different amount of water. Public use means the water it uses in the public building or public services. For example, the water for city fire protections, or the flushing the street cleaning, or some public building like a bus terminal, or probably the airports, something like this. So this kind of public use may be accounted water use in this public places may be accounted for 50 to 75 liters per capita per day, including the fire protections. Loss and waste are the amount of water that we produced. Sometimes during transportations, during sending through the piping system, there may be a leakage. So there will be definitely some lost. Every cities all over the world, there may be some loss, but the amount of loss and waste depending on the how they maintain the distribution system. Recently, I've met the people from the waterwork authorities. They said in Bangkok and the suburban areas, the waterwork authority, they have lost as much as 30% of water produced to the due to the leakage. So 30% is quite a lot. But in some city with the good public plumbing code, good maintenance for the piping system, they may reduce this part to be less than 20%. In Bangkok, there are 4 or 5 large water treatment plants, and the biggest one is located in Bang Khen. I'm not sure, but we generally call Bang Khen water treatment plant. I don't know exactly where it's located, which district it located, but we generally call Bang Khen. This plant they produce up to 3.2 million cubic meters per day. So just imagine they have lost 30% of water producers every day. So how large in terms of the volumes can you just imagine? So 30% every day is due to the leakage, not due to the unauthorized use. For the electricity, there may be little unauthorized use, but for water, it's rarely. We normally don't find it in Thailand. Mostly, it's depend on the poor operations and maintenance in some certain part of the distribution system. That is why the loss and waste is quite a lot, 30%. But if we consider like a country like Singapore, this country is very small, little bigger than the Phuket Islands, the entire country. In terms of the size, it's little bigger than the Phuket Island, but they have very good operation and maintenance system, not just the water treatment plant, but they also taking care of the distribution system in the entire island. So they can actually minimize the loss and waste to be less than 10%, 5 to 8% only. Maybe the system is just very small. That is why it's easy to maintain. So it's easy to look into the problems and trying to solve the problems immediately. That is the in case of the country where they can actually will manage the system. Factor affecting water use. As I mentioned, there are many factors that could affect the behavior of or the developers who live in the communities. The amount of water use depends on the size of the communities and whether there are some industry presence in the communities areas or not. The qualities of the water. So if the qualities of water it's good, people tend to use more water in their daily life. But if they just turn on the taps water valve and then they get a color and they get some turbidity in the water, so they feel the water may be unsafe for the consumption. So in that case, the people trying to avoid using the water. So in that case, we see a less amounts of water uses in their daily life. Its cost, of course, if the community they charge more price, so people try to use a less amount of water. Its pressure, so pressure should be maintained according to the criteria of the water distribution system. The pressure in the piping system should be maintained at around 1.5 bar, 1.5 bar, which is quite enough to supply water to the second floors. So if your house has 2 floors, so with the normal pressure, it should be able to supply up to the second floors. So 1.5 is quite enough for the pressure in the distribution system. But in fact, in Bangkok and many municipalities, the pressure is quite low, especially during a high demand in the morning and in the evening. So the pressure never reached 1.5. So generally we could find like a 0.5 bars only. 1 bar it's equivalent to the water column's height 10 meters. If you still remember, 1 bar equivalent to the water column's height 10 meters. So in fact, 1 bar, if we don't include the pipe lost, so it should be able to supply up to the third floors. But in fact, it's not possible because due to the loss, due to the actual pressure that we have found in the water distribution system never reach the suggested criteria. The climate. So if you are living in the cold climate, people tend to take a shower just once a day. In the Europe, people they take a shower maybe once a week, so it really happened like that. But in Asia, we prefer to take a shower at least one time per day. In Bangkok, generally people take a shower 2 times per day, morning and evening. One of my friends, she got married with a German guy, and she moved there. And after staying there for a few weeks, so she has a conflict with her husband families on the issue of water used. Do you know why? The families they are not happy that my friends she take a shower in the morning. uh, even even the temperature gets close to zero, she still take a shower in the morning in Germany. So it's become like we get used to, right? So we take a shower twice a day. That is very common for us. We don't feel comfortable if we don't take a shower in the morning. So that is a kind of the so if you go there and then try to adjust your behavior, try to adopt the way they live, then uh, it will be easy to enjoy the families or enjoy with the new conditions of the new environment. Okay, anyway, the climate could be one of the factors that change the water use pattern, that cause the difference in terms of the water use patterns. Characteristic of the populations, the youngster or the working man tends to use more water as compared to the elderly, because elderly they just stay at home, they don't have much activity to do, so water use will be less. Weather supply are meters. For example, if you're staying in the Asian Games village inside the campus, Thammasat University campus, I think you will be charged for the water used per head per month. You are supposed to pay, for example, 200 baht per month, per head per month, no matter how much you use the water. So if you used more, you still have to pay 200 baht. If you use less, you still have to pay 200 baht. So it's a fixed price. But if you are staying in some dormitory outside, they may charge you per volumes of the water used per cubic meters. So if you use more, they will charge you more. So if there is a system of equipping with the meter, just like the provincial waterworks authorities or metropolitan waterworks authorities, they do. So they install the meters at every houses, so they know the volumes of the water used. Then if the house use more water, then they have to pay more. That is the system of meters that they use to manage the water used. But in our case, if we are staying in the Asian Games village, so you will be charged per head. So according to behavior, if you review yourself, you will find like you don't care how much of water you use. Sometimes there is the leakage, so you just let it go. So after a few days, maybe you will call the staff to fix it. So you don't care about the water loss, so you don't care about the leakage. So you used water as much as you want. That is a kind of, we don't have meters, like we already pay for lump sum. So this is a kind of, one of the strategies that could actually enhance the people to use less quantities of water. So if there's the meter. And the other thing is the efficiency which the systems is maintained. So as I mentioned, so if the we could do a proper maintenance. We can minimize the loss and waste. So we can minimize, we can reduce the amount of water that leak due to the poor piping conditions. So these are all the factors that may affect the water use. So if you really take a look into the community, you will find for the domestic demand, the people may use up to 300 liters per capita per day. So these are just the one example. The percentage of total may be varied depending on the activity in the community, and it may also vary from one community to other community. Industry may be up to 160 liters per capita per day, and loss and waste may be just 8% of the total. So entire water used per head or per capita for this community is 670 liters per capita per day, but only 300 for the domestic use or for the human activity, not much higher. Size, characteristic of the population. So this we have already mentioned. In the household, the people may use the water mainly for the toilet flushing and for showering. So if you take a bath, it may be less than 30 liters per capita per day. But if you take a shower, it may be 30 or sometimes it's even higher. Cooking is only 5 liters. Drinking, you are recommended for good health. You should at least drink 3 liters of water per day, or equivalent to 2 big plastic bottle. So one plastic bottle, the big one, consists of 1.5 liters of water. So you should finish 2 bottles per day, at least 2 bottles per day. For washing, generally speaking, people may use up to 15 liters per day. Cleaning, another 15 liters per capita per day. So totally maybe around 100 liters per capita per day. Anyway, this is just one of the example for water use in various purposes. These are the information showing the domestic water used in various types of accommodations for the residential areas. High income people, they may use up to 380. Lower income maybe 270. These are the residential areas, but for some places like a hotel, people just go there, stay there for the temporary visit. Then the amount of water used may be up to 300 liter per room per day. So the far right columns is the water used divided in terms of the liters per unit per day. So the units are given here in the second columns. Apartment for temporary stay, the amount of water used is 150 liter per capita per day. The office, 70 liters per capita per day. A massage and spa, the water used is around 100 liter per a customer per day. Gasoline stations, there may be up to 40 liter per car. So these are the average water used at this placed. Our hospital, the water used is 950 liter per bed per day. In the hospital, they use a lot of water for hygienic purposes. That is why, in terms of the water used, they consume up to 950 liter per bed. Actually, per one bed, it's one patient. Generally speaking, we can say like it's 950 liters per capita per day for the hospital. Other types of the business, like a restaurant, they may use up to 30 liters per customer per day. So these are the information you can make use if you want to estimate the amount of water used in various types of the business or industry. This table describes the water used at various industry, canning industry, milk productions, craft pulp, chemicals productions, slaughterhouse, liquor, beer, brewing and dyeing. So these are the types of the industry. Mostly the water used expresses in terms of the liters per units. Units is the tons of the products. So if they want, if they produce like at the canning industry, if they produced the products which around 1,000 tons per week, so the amount of water used is you have to take this one, multiply it by the wage. So of the wage of the products. So this is how we estimate water use at the domestic and the industry. Another thing is that for the water use, there will definitely be the variations. So I'd like to show you the variations of the water used in various community. Why it choose this one? Okay. Here, in fact, these pictures I was searching from the internet, but anyway, I was supposed to show you this one in the class. Okay, this figure, actually this figure was taken from the water supply and pollution control textbook by a wise man. I think you can find this reference in the library. So if they allow you to get into the universities and use the library, so you can look for this textbook, and inside there's a lot of information about the water supply and sanitary engineering. But anyway, what I'd like to show you is this graph. So this graph shows the daily water use pattern. So in the morning, not much water is used, but in the evening, especially during the maximum day demand, the peak flow or the peak demand could actually as high as above 2,000 gallon per dwelling units. This one is the dwelling unit, so not per head. Okay, but anyway, it gives you a figures of the at what time the people use a lot of water. So the peak demand normally take place around in between 7 to 8 p.m. in the evening. People use a lot of water at just before 8. But in the winter, so the water use pattern it's totally different. People use less than 400 gallons per dwelling per day, but the peak is also occur at in between 7 to 8 p.m. in the evening, but the demand is not as high as the maximum day, which I assume this will occur during the summer when the temperature is high. The people tend to use more water. This one is the daily water used pattern. What about this one? This is also taken from the same textbook. In fact, I have this textbook, but as you know, now I'm not in the office, so that is why I have to search this figure from the internet, and I finally found this is also the daily water use pattern, but it shows the water use in winter and in the rainy day. The water used during the rainy day, so it's just the same as during the winter. So with the rains, the people use less than 400 gallons per dwelling per day. But if there's no rain, it may goes up to almost 1,600 gallons per dwelling units per day. So these are something different. But anyway, you will see something like there's a variations from the lowest to the highest, and it goes down again during the late night and early morning. So the water use pattern in the communities will be always like this. So according to this, you see that some variations. There's water variations over 1 day during the periods of 1 day. During the periods of 1 week, there will be also water variations. During 1 month, there will be also the water used variations. During 1 year, there will be also the water used variations. So as the water variation is aware, what we are really interested, we are really interested in the average used or the average demand. So how we can estimate the average demand according to this figure? How we can estimate the average demand according to this figure? So what does this figure tell you? So over the period of 24 hours, so within 1 day, the class begins from the 12 a.m. in the night time, and then ended at 12 a.m. in the night times again. But anyway, it shows the water use variations over the 24 hours. So if you want to take the average flow over the periods of 1 day, so what you can do, you have to take the summations of all the flows occurred in these 24 hours. And then you divide it by 24, so you get the average demand or the average flow rate. Okay, so in fact, the water use or the demand is the flow rate. Okay, so if you take like a summations of the flows divided by 24, you definitely get the average demand. So that is called the average. Okay, but for the maximum demand, which occur at around in between 7 to 8 p.m., this one we generally call a peak demand or the peak flow, P-E-A-K. Okay, it's the peak demand or the peak flow. But here at 4 a.m., nobody used water, or if they use, it's just very small quantity. So here is the minimum demand. Okay, so we have peak flow or maximum flows, average flow. Then we have the minimum demands of the lowest demand. So we're really interested at these three types of the demands: peak flows, average flows, and minimum flows. Why we are interested? Because our system, if we are going to design the water supply system or water treatment plant, so the plant should actually process or supply water at various flows according to the demand. even at the low demand, water treatment plant should provide the water. And even in maximum demand, so much different, this water treatment plant should also be able to supply water to the community. So that is why we need to know all this information, wide variations, average flow. Why we really need to know the average flow? Because the average flows will tell you about the, for example, the chemicals during water production. Sometimes we have to use the chemicals. Sometimes we have to apply the chemicals. The chemicals like alums or maybe a chlorine. So these are all the chemicals commonly used in the water treatment plant. So we need to know various type of flows to supply a sufficient amount of chemical. So in order to know the amount of the chemical used in one day or in 1 month, we need information about the flow. And the flows that we pick up to estimate the amount of chemical used is the average flow. Okay, so we need the average flow to estimate the chemicals requirement. We need to know the peak flow to design the pumping facility, because the pumps should be able to supply during a highest demand and also should be supplied during a lowest demand. So we need to decide the system. So in terms of the flow pattern, we need to know everything. But the thing is, according to this figure, what about water variations in probably in Bangkok? So it may look like this. So I'm now on the screen of OneNote. Hopefully you are with my OneNote page. Okay, so in Bangkok, maybe like this. So little increase in terms of the water use during the morning, and again increased before it gets lower again during a period of 24 hours. Midnight to midnight again, and this one may be at noon, 12 p.m. Okay, so this one is generally called Q peak, and this one is the average flow. So average flow, it's a flow where we take the summations of the flows in each hours divided by 24, like this. This is the average flow, and here maybe the minimum flow. So the pumps should actually be able to manage or supply flows from lowest to the highest. So in order to design the pumping facilities, we need this information, Q peak and the minimum flows. There is one more thing we need to know is the peak factor. Normally, when we talk about the water use 300 per liters per capita, 300 liters per capita per day, 200 liters per capita per day, it means we are talking about the average flows, okay? We are talking about the average flows. If you said like we are using 150 liters per capita per day, that is the average flows. But anyway, during the peak demand, the water use increased a lot as compared to the average demand. Generally, it is like that. So if you want to estimate the Q peaks, you may really need to know the factors called the peak factors. If you are taking Q peak divided by Q average. Now, of course, as Q peak is greater than the Q average, so what will be the amount? So at least it will be greater than 1. So this ratio, the peak factors and the average, the peak flows and the average flows. So if you are taking Q peak divided by the Q average, so you will definitely get some number greater than 1. Okay, and this amount is generally called a peak factor. Okay, so this is the peak factors. So peak factors could be estimated from the graphs. If you already have like a information regarding to the flow variation, you can determine a Q peak easily. You can determine a peak factor easily. But if you don't have the information about the peak factors, you will not be able to determine the peak flow. So in that case, what we can do, peak factors can be determined from the Q peak divided by the Q average. But if the peak factor is not there, suppose we are going to design the new plants which never been built before in this community. So you don't have the statistical record. You don't have any idea about the ratio between the Q peak and the Q average. If you don't have anything, you have zero information. So in that case, how you would estimate the peak factor? So if you know the peak factor, you can multiply it by the Q average. You will definitely get the Q peak. Q peak is equal to peak factor. So in short, I would just write a PF, which stands for a peak factor. Peak factor multiplied by the Q average. So you finally get a Q peak. Okay. If you know the peak factor, you can multiply the peak factor by the Q average. You will finally get the Q peak. But if you don't have this information, if you don't have the peak factors information, you don't have any idea because the statistical record never been exist, especially for the new community. So in that case, the engineer is recommended to use these formulas to determine the peak factor. Okay, what is this formulas? This formula is called a Goodrich formulas. So I'm now on the screen of my PowerPoint. So hopefully you are with my PowerPoint screen right now. If you don't have any information about the peak factor, you can use the Goodrich formulas. So what is the Goodrich formulas? Goodrich formulas is the formulas we use to estimate the percentage of the annual average which occur during the charter periods. Or on the other hand, we can say that this P is the peak factor. Okay, so how we can estimate this peak factor? So peak factor is equal to 180 into T to the power of minus 0.1. Okay, but this one is expressed in terms of the percentage, not the decimal number in the previous case. So if the peak factors is like a 3, average floats is 1.5. So in that case, we can say that the peak factors is at least 2. Okay, in that case, 1.5, 2. So that these are the decimal number showing the peak factors informations. But in this Goodrich formulas, the peak factor is expressed in terms of the percentage. What is T? T is the length of the periods in the day, ranking from 1/12 days to 360 days, not 365, 360 days only. So this information valid only when the t is starting from 1/12 day to 360 day. Okay, so 1/12, what does it mean? This is the minimum value. 1/12 days means 2 hours. The peak that occurs over 2 hours. This is the minimum dates. And then 360 days, that could be a length of the period. So if you are asked to estimate the percentage of annual average of the during the periods of 1 year, you should actually use times t equal to 360, not 365. Okay, so if you put all this number into this formula, for example, maximum day t is given as one day. Okay, so if it's 1 day, so what will be the value of p? So if this is 1, so what will be the values of p? 1 to the power of minus 0.1, it's 1 anyway. So a p is equal to 180%. So 180% or 1.8 with respect to the average flow. Okay, so this is how we can use these formulas. These formulas is called a Goodrich formula. So it's basically the empirical formulas. It's an empirical formula, so not the homogeneous equations. This table shows the comparisons between water variation in the municipality, the percentage of the annual average. So this one is collected from the statistical record. So if you want to find the daily average in a maximum month, you may substitute like a t is 30, because now we are talking about the average in the maximum month. So in that case, we have to substitute the equation by 30, and finally you will get 108. So for the daily average in maximum week, the time, it's 7 day. So we just submit 7 into the these formulas. So finally you get the percentage of annual average. For 30 days, you will get 128%. For 1 day, you get 148%. Maximum day in a year, so just substitute by 1. Peak hour within a day, you can take 2 divided by 24, which is the minimum values for this equation. So less than this or greater than 360, this equation will not be valid. But anyway, if you already have the statistical record, you don't have to use the peak factor determinant from the Goodrich formulas. Looking at the statistical record is much better. So in this table, it shows the comparison between the statistical record and the one which we derived or gained from the equation. A percentage of the annual average from the equation, if the time it's 30 days, so that the percentage of the annual average is after substituting all this, you will find the percentage. If you consider a peak factor, so this will be 1.28. This will be 1.48, and this one maximum day in a year. So this one is 180. Just substitute into the Goodrich formulas. And then if you compare to the statistical record, you will find it's not much difference. For example, daily average in maximum month from the statistical recorded, it shows the rank. Water use may be varied depending on season, depending on other factors. The range 110 to 140. The typical value that we can pick up from this range is 120. So if you compare to the one which you calculated from the uh, equations, Goodrich formulas, you will get the percentage of annual average around 128, which is very close to the actual situations or actual statistical recorded, because the actual statistical recorded we have already get 120. But if you are using the formulas, you will get the flows slightly higher than the normal. Okay, so these are the variations in water used. As I told you, if we already have the information, then we use the information from the statistical record. But if we don't have, we can just use the values obtained from the equation. This is also possible. But be careful, the peak hour within a day are totally different from the percentage of the annual average. The peak hour within a day may goes up to 270, but from the equation, it may be around to 31 only. So it's a totally different comparing between the statistical recorded and the value that we obtained from the equation. Another thing is whenever we estimate the water used, we have to consider the water that we have to store it for fire protections. According to the National Board for Fire Underwriter in the US, they have launched the criteria. So as I mentioned, the criteria, it's not legally enforceable. It's not the standard. So criteria may be obtained from the statistical recorded. But anyway, from the records, this organization, National Boards for Fire Underwriter, they have developed these equations and how we can make use of these equations. So we use this equation to estimate the demand required in the downtown business district. You can estimate the water uses for fire demand by using this formula. Again, the same as the Goodrich formulas. These formulas is not the homogeneous equation, so you have to be careful about the unit. How can we use these equations? These equations is the fire flow, is the fire demand. The Q here is the fire flow, so the fire demand over 24 hours. P is the populations in thousands. So just substitute the populations in thousands into this equation. So in that case, Q will be equal to 3.86 square root P. P is the populations in thousands minus 1 minus 0.01 square root P again. P is the population in thousands. So you can use this equation to evaluate the fire demands in the community. But anyway, there's a remark. the output that you have gotten from the calculation Q, the fire flow rates, and the Q is designated as cubic meters per minute, cannot be other units. Okay, whatever you calculated from this equation, the unit must be follow. You must follow the. You don't have to consider the unit. Okay, this one is the populations in thousands, so Q is cubic meters per minute. But anyway, this one is the flow rate for a period over 24 hours. But in fact, the fire, whenever it gets burned or it gets exported, there's a fire. But the fires, in fact, never last for a day or 24 hours. Mostly within 10 hours, the fires in general could be completely controlled. That is why whenever we get the value from this equation, we have to adjust again. So this one is with respect to 24 hours. But the fact, according to the fact, fire never lasts longer than 4 hours. So in that case, the fire flow rates, we have to adjust whatever the values we have gotten from this equation. You have to multiply by properly 10 divided by 24. So if you think the fire would last for 10 hours, you have to multiply by 10 divided by 24. Or if you think the fire maximum would last for like 6 hours, you may take like the value you have got from this equation, you multiply by 6 divided by 24. So this is also possible. This equation is actually for the used for the fire flow estimation in the community. You can see that we substitute the number of the population, then you get the flow rate. But on the other hand, in the building, if you want to determine the required fire flow, again, in the building, so as you are environmental engineer, probably one day you may have to decide, you have to determine the amount of water used to control fires in the building. So what you can do, the building, it's not, with respect to the population in thousands, but there's a different way of determination for the building. Mostly the amount of required fire flow depends on the total flow areas. It depends on the total flow areas. If we have like a more areas, more flow area, you will have to store more water. So this is kind of how we can determine the fire demand within the building. But be careful, the unit is cubic meters per day for a fire flow. The total floor area is given as square meters. C is the coefficients related to the types of the construction. If our building is made from wood, then C should be equal to 1.8. And if it's just the ordinary constructions, what C value you have to use? You have to use only 1. For non-combustible construction, C would be 0.8, and for a fire resistive construction, C could be 0.6 only. So it depends on the types of the constructions. It depends on the types of material used. The one which is easy to catch the fires, then we have to provide more water. That is why C values here they put up to 1.5. Okay, so this is a kind of 5 floats estimation. In the next slide, it's also the same equation as I have just described last slide, this one. The required 5 flows in this equation must be expressed in terms of gallon per minute. If you want to convert the gallons into liters, you have to multiply by 3.8 or 3.78. Okay, but there's a mistake here, so you'd have to put a dot here in between 3 and 8 because it's the conversion factor. 1 gallon is equivalent to 3.8, 3.8 only. Okay, not 38. Okay, air is a square foot. Here there is also a mistake, so please correct it. Square feet. Flow areas may be expressed in terms of square meters, but 1 square meters is equivalent to 10.76 square feet. So just apply this conversion factor before determine from this equation. Okay. Anyway, these two equations, both 320 and 18, actually they are both the same equation, but you see some value different, 320 and 18. So changes or the difference in this number is due to the unit. So different unit definitely gives a different number. So don't be confused. Anyway, both are the same equation. For the file demand, based on this equation, so if you have a large flow areas, the file flow will be greater accordingly. So if you have large flow areas, but anyway, for the storage buildings, the areas is quite large. But in fact, if you really consider how the fires would occur, the fires would occur at some places, but it's really difficult or very is small chance to occur all over the building. So it's originated at some point, at somewhere in the building, but not all over the area. So if we calculate from these equations, you may get the value like a higher. This equation it's recommending you to use only the maximum value. For example, for a single story structure, whatever the value you have got from the calculation, you can only use up to 600 gallons per minute. Okay, 6,000 gallons per minute. If you get after the calculation, you get like a 9,000 gallons per minute, and it is a single story structure. So if you get like at 9,000, you can minimize. You can use only up to 6,000 gallons per minute. So just pick 6,000 gallons per minute. Don't use 9,000. 9,000 would be too large, or 8,000 for a single building. For a single building, the building with many story. But in case if the building is located just next to another building, which also has a very high chance of getting, a fire. In that case, the building may have to supply some amount of water to help the neighbor building to control the fire. So in that case, the maximum fire demand could go a little bit up to the 12,000 gallons per minute, but shouldn't be higher than 12,000 gallons per minute. So what I'd like to say is this information, whatever the value you have got, that is the minimum value, it should be 500 gallons per minute. According to the calculations, if you get 480, so you have to use 500 gallons per minute, like that. So this is how we can apply this equation, and it shouldn't be greater than 6,000 for a single story structures, 8,000 for a single building, and 12,000 gallons per minute for the supplying the building to the neighboring building. So this is like the range of the fire demand supplying to the each individual building. Or as I mentioned in the previous equation, a fire flow we maintain up to 10 hours. For the determinations of the fire demand in the building, we also consider the fire durations. The fire duration is the same, should not be greater than 10 hours. So within the 10 hours, 99% of the fire can be controlled. So anyway, whatever the values you have got from this equation, you will still have to reduce according to the fact here. The maximum duration 10 hours, but never longer than 10 hours. Okay, so whatever the value you have got, you have to multiply by, for example, 10 divided by 24, or 7 divided by 24, like that. So we will see again in the example. According to these two aspects, the Goodrich formulas and the fire demand, then I'd like to discuss about the example. Let us begin with the example 3. In the example 3, determine the maximum water demand during a fire if it is assumed that a community with a population of 12,000 has the average consumption of 600 liters per capita per day, and a fire flow dictated by a building of ordinary construction. For the ordinary construction, the coefficient related to the types of the constructions. For the ordinary construction, C must be 1. Okay, C must be a 1. And then what is next? The information provided by this example, according to the fire, okay, this building, this is basically a 6-story building. Each building has each stories has a floor areas of 1,000 square meters. The fire flow must be maintained for 10 hours. So estimate the average domestic demand, a maximum daily demand, and maximum rates, including the fire demand. Okay, we'll go to this one by one. Average domestic demand. The average domestic demand, it's basically equal to the populations into the average consumption. Here, the populations of 20,000 and the average consumption is 600 liters per capita per day. So that we can find the average domestic demand, which is equal to 22,000 into 600. So this will be 13.2 actually million liters per day, 13.2 million liter per day. Okay, for the maximum daily demand, here the question is asking for the peak flow. Do you still remember for the peak flow? A peak flow is the maximum flows which occurs over a period. Then for this, if you multiply the peak flow by the average flows, you will get the maximum daily demand, or the Q peak. In this case, as we are concerning about the maximum daily demand in the Goodrich formulas, suppose you don't have any information about the water use in this community, so you have to try to find the information by yourself. So if you don't have any information, what you could do, you may use the Goodrich formula to determine the peak factor. And as we are about to find the maximum daily demand, so the length of the periods in this equation should be 1. So if you substitute T by 1, you will get P 180%, 180%, or in terms of the ratio, it is 1.8. Okay, it is 1.8. Then just come back to these examples again. Example 3. Maximum daily demand could be average domestic demand set into a peak factor, or the peak demand. The ratio between the peak factors and the average demand, it's 1.8. It's 1.8. So according to the Goodrich formulas, it's just you substitute the Goodrich formulas by 1. So you will get P equal to 1.8. That is why if we take the average into the peak flows, which is equal to 1.8, you will get the maximum daily demand, which is about 23.8 million gallon, million liter per day. Okay. Then for the fire demand, if I just pick this equation to find the fire demand, you will find the fire demand as high as 24.9 million gallon. Million liter per day, quite a lot, million liter per day for a fire demand. We have 6 stories. Each story has like 1,000 square meters, and 10.76 is nothing but just the conversion factor. Okay. Finally, we get the fire demand approximately 24.9 million liter per day. And if you're about to determine the maximum rate must be equal to the maximum daily demand plus the fire demand. The maximum daily demand is clearly get 23.8 but the fire demand you have to manipulate this number, as this number is with respect to 24 hours fire continuing occur, but in fact we can actually control it within 10 hours. That is why, according to this question, maximum rate is equal to 23.8 into 24.9, but this 24.9 you have to reduce this somehow, because finally the maximum rate is 34.2 million liters per day. Okay, so these are the examples related to the Goodrich formulas and also the fire demand or fire protection. Do you have any question regarding to this example before we move to another example?
อาจารย์ครับทำไม P ถึงเป็น 1.8 นะครับทำไมเราถึง
P
ใช้เป็น1 day
it's the maximum daily demand, as is the maximum daily demand. That is why P is 1.
อ๋อเป็น daily ก็คือเป็น1วันใช่ไหมครับ
ครับ
ขอบคุณครับ
ครับ maximum day in a year, so T is 1. Daily average in a maximum week, you should use 7. If it is a daily average in a maximum month, you should actually put 30, substitute the T by 30. So it depends on what you're going to determine. Okay, the conditions are different. Any other question?
ครับแล้ว 10.76 มายังไงครับอาจารย์
10.76 is the conversion factor. It is the conversion factor. As we are using these formulas, right? Fire flow is given as gallon per minute, and the total floor area must be in terms of square feet. เลข2นะไม่ใช่ตัว S นะอันนี้ต้องเป็น 3.8 ไม่ใช่ 38 นะฮะplease correct นะฮะ there's a mistake here and here. Conversion from square meters, the question give like a 1,000 square meters, but in this equation we have to use in terms of square feet. In this case we have to multiply by 10 to 0.76. This is just the conversion factor. Okay, otherwise if you prefer the SI unit, you can use this equation 320 C ความจริงคือ square root A นะฮะอันนี้ก็cubic meters to the power of 3 m to the power of 3 but due to the limitations of typing in my computer, I have no choice, so I have to put it like this. ไม่รู้มันอยู่ตรงไหนนะฮะคอมพิวเตอร์ผมเนี่ยมันพิมพ์แบบ Microsoft Word ตรงๆไม่ได้ต้องไปใช้ Microsoft Word ต่างหากนะครับแล้วก็ copy เข้ามานะฮะก็เลยดูมีหน้าตาแปลกๆนะครับ
ใช่ครับถ้าอย่างนั้นเราใช้โปรแกรมที่เป็น320ได้ไหมครับ
It's possible ใช่ได้ฮะ
แทนค่าออกมามันจะเท่ากันใช่ไหมครับ
supposed to be the same นะฮะoutput
แต่ว่าอันนี้ไม่ต้องแปลงหน่วย
ไม่ต้องใช่แต่ว่าไอ้ตัวนี้มันก็ต้องต่อวันท้ายสุดคุณก็ต้องมาทอนให้เหลืออยู่10ชั่วโมงหรือกี่ชั่วโมงก็แล้วแต่อีกอยู่ดีนะครับ10ชั่วโมงนี้ไม่ได้ตายตัวนะมันอยู่ที่เราเลือกแล้วเราอธิบายนะฮะครับเมื่อกี้ใครว่าอะไรนะฮะอีกคนนึง
จ้ะครับแล้วตรง 1,000 คูณ 6เพราะมันมี6อันนั้นใช่ไหมจ๊ะ
6 stories 6ชั้นนะครับ A คือ total floor areas นะฮะeach floor consists of the areas of 1,000 square meters. A height of 6 story คูณ 6 ก็เพราะว่า we have 6 stories height building. โอ้แสดงว่ามีคนนั่งฟังอยู่นะเนี่ยนะฮะไม่ใช่ผมพูดคนเดียวนะ so after conducting the lectures for almost 1.5 hours. At least somebody has listened or paying some attention. Okay, then we move back to the first example. So the first example, this morning is actually it's the day that we pray for the God and our ancestors. I don't know what about you, but to me, we also have these traditions in our house, especially today. We have to wake up at 4:30 to prepare everything. then we pray early morning, and after having a breakfast, then come to the class. But luckily, we have class at home. Otherwise, if we have classes at the universities, so I have to run for the 2 days. Okay, for the first example, just come back to the example 1 again. For the example 1, it's a situation that is why the question, the information provided in this question is quite long. You shouldn't expect the question will be like the question you're familiar in structural analysis or the mechanics, engineering mechanics. The question is the situation. So we give you the situation, then you just find the solution. So there is no like a sometimes the situation that we give does not have only one answer. There may be several answers, but you have to judge which one is the best for the solution for this situation. Okay, so the question in this course generally it's like that. There may be many solutions, okay, which are correct. Okay. Okay. For the example 1, a community having a population of 250,000 in a year 2000 estimates that if the populations, it is estimated that its population will increase to 400 by the year 2020. I'm showing the example 1 on my screen. Hopefully you would also see this page, not just my face. The treatment facility in place can process up to 55 million gallon per day. 55 million gallon per day. MGD, it's a million gallon per day. The 2000 per capita water use rate was found to be 160 gallon per capita per day. Suppose we are in a year 2000s. Okay. Suppose we are in a year 2000s. 2020, it's in the future. Okay. Or this one should be 2020, and then this one should be 2040. Estimate the water requirement for the community in 2020, assuming that the per capita use rate remain unchanged. So now the first question comes to estimate the water requirements for the community in 2020, assuming the per capita use rate remain unchanged. So the per capita use is 160 gallon per capita per day. So what will happen to the water consumptions in year 2020 as the populations increase from 250 to 400,000? So for 400,000, the per capita use still 160. So just multiply. What you will definitely get, you will get the water use in this year about 64 million gallon per day. 64 million gallon per day. Remember that 1 gallon is equivalent to 3.78 or 3.8 liter. The question, okay, so in the next sentence, this is the question. Will new treatment facilities be needed to accommodate this growth in populations? The current water treatment facilities can process up to only 55, but in year 2000, we require 64 million gallon per day. So much different. That is why, with respect to this condition, new treatment facility should be needed for this year with the same conditions. The water requirement, new facilities, treatment facilities, or at least the expansions of the production capacities is required for year 2020. But anyway, another option, if revised pumping code were adopted during the periods of growth, and after adoption, if these changes results in an overall reductions in the community's water use by 15%, what would be the water requirement in year 2020? So revised pumping code, for example, code of practice may be launched and suggest the operator to change the pipe regularly. Before they had never changed until it break. Then the code is used. The code recommended to change every 10 years. For example, so if it is every 10 years, then the pipe are maintained in a good conditions. In that case, loss and waste, it can be minimized. So this is just one of the example of the new plumbing code, which affects the performance or affects the maintenance schedule to the distribution system. That is why a loss and waste can be minimized. So if loss and waste can be minimized, then 15% of the water used can be achieved. In that case, currently the people in this community use up to 160. So 15% reduction, it remains only, so it reduced to only 136 ไม่มีจุดนะฮะ 136 gallons per capita per day. So if it's just 136 gallons per capita per day, and in 2020, a population forecast would be 400,000. So in this case, if we could reduce the amount of water used, the water requirement for the entire community would be only 54.4 million gallons per day. Then what is the question? Could the expansions of the treatment facility be deferred? There is no need, because now it comes below 55 million gallons per day already. So this conditions, we can actually prolong periods of the constructing the new treatment facilities or the expansions of the new treatment plant. So this is the situations. Okay, you may find out the solution somehow. This is the solutions to the example 1. Do you have any question regarding to this question? This questions is quite straightforward. And then, if no, then let us move to the another example. Another example. The example 2. Example 2 is also another situation. Someone had just has not turned off the microphone. There is noise. Okay. This periods, it's elections periods again. The local municipality, they have planned to go for the elections by the end of by the end of March, and this time many truck announcer, they move around to encourage the people vote for them. Sometimes it's very noisy. Sometimes it moves very close to my place. So it's really disturbing. Okay, anyway, the second example, it's another situation. Consider that in 2000, a state had a total water withdrawal of 8 billion gallons per day. Unfortunately, this example and also the previous example I have taken from the textbook. I think it's also Weizmann textbook, Water Supply and Pollution Control. This textbook was published in the US, so that the units are explicit. They mostly use the US customary unit. They don't use the SI unit. But in the exam, in the probably in the assignment, so I'll give you the question with the SI unit. But anyway, it's good to be familiar with both the unit. In Thailand, in your generation, I think mostly you have only studied the SI unit. But for me, I have to do both. So sometimes it's very confusing doing both the units, because when I was the student, mostly the textbooks come from the US or the UK. That is why we are really familiar with the unit conversion. Sometimes we need to get like a table with lots of the conversion factor. So if we want to convert the units, so we just check, we just pick the number from the table. So we need to have like one book containing just the conversion factors. It must be always in the back whenever I go to the universities at that time. But by the way, just come back to this example again. Or in the year 2000, water withdrawal. Water withdrawal. withdraw นี่แปลว่าสูบน้ำนะฮะ in this context เนี่ยนะฮะแปลว่าสูบน้ำนะฮะ water withdrawal of 8 billion gallons per day. So this community basically consumes 8 billion gallons per day, distributed as follows. Municipal water use 1 billion gallons per day. And very interesting, this community, they also use the water for a stream electric generation, 5 billion gallons per day. Why? Do you know why? That stream electric generation require lots of water. They need water. They need to use the water for cooling, right? And mostly, if they really wants to look at the power plants, they will decide the location where it is close to the water resources. So especially the nuclear power plant needs a lot of water. The location they prefer, they would select the location which close to the water resources. They don't put it in the dried areas. Northeastern part of Thailand, sometimes there is a water shortage. They will definitely not locate the nuclear power plant. The nuclear power plant we have been discussing a lot in the past, but now it seems like the government agency, they are not interested anymore, especially after the nuclear power plant leakage after the tsunami in 2004. And also in the Russia several years ago. Now the people are really aware and are scared of the disaster. Okay, then irrigated agriculture, 2 billion gallon per day. Basically, 3 sectors consumes 8 BGD. In 2000s, the population was 7 million. By the year 2020, it is expected the population will increase up to 13.2. And in year 2020, there will be new electric generation capacity be installed. 4,000 megawatt, quite big units. And then for the agricultural areas, the irrigated acreage we expanded by 500 acres. 500 acres. The question is, estimate the total withdrawal in next 20 years. Suppose we are now in year 2020. Hey, year 2020 is the year that some students were born, I think, or maybe around this year. But it's the year I think I graduate from the universities 20 years ago. Okay. The withdrawal for each 3 sector, you really need to study. According to this situation, you really need to study. Okay, like for the human consumption in this community, how many liters of water they consumes. That is for the first sector, and then second, you have to study again for 4,000 megawatt. What kind of equipment they will use? The equipment that they used, how much water it's required, like that. Then for the third sector, agriculture, the allocated acreage or area we expanded by 500,000 acres. These expanded areas, what types of plant they planted to cultivate or to grow up. So each types of plants, they require different amount of water. So if you are going to plant a sugarcane, you may need less of water. So if you want to turn this area to become a rice paddy field, you need a lot of water. So from this situation, we need to study further. And again, once we study, we take that information and estimate the total water withdrawal for each sector send the total withdrawal in a year 2020. So after studying, we can predict the amount of water used. For the domestic use, it is expected the people, they use up to 140 gallons per capita per day. And according to the populations in the year 2020, so about 1.5 million populations increased. So in the year 2020, we need another 210 million gallon per day. At the moment, we use up to 1 billion gallon per day. Then the next 20 years, we need another 0.21 billion gallon per day. So it becomes 121 billion gallon per day for the municipal water used. And then what about the agriculture? Agriculture, you may consider like this. Crops to be raised average. This is the amount of water required for the crops. As I mentioned, you may have to look into what types of the crops, what types of the plants they plant to raise. So if you know the types, you can predict how much water we need to supply. So if they know the types of plants, then they know the amount of water. So in these questions, the amount of water that is required is about 3 acre-feet per acre. Don't be wonder about the unit. Okay, it's just the volumes per areas. Acre, it's area. Okay. In Thailand, maybe the areas we generally call, we generally refers to rai, but in the U.S. customary unit, maybe they like to express in terms of acres. In SI units, of course, you are really familiar. You may are expressed in terms of the square meter. Okay. But according to this water requirement, 3 acre-feet per acre. Acre is the area. Feet is the depth. Feet is the depth. Okay. For example, if you want to determine the amount of water, rainwater, entering to this catchment area, what you can estimate, how you can estimate this, the amount of water. You have to take the rainfall intensity I and multiply by the areas A. Okay, this is just similar to the rainfall intensity, millimeters per hours, like that. And this is the areas. So areas into the height is the volume. Areas into the height is the volumes. So basically, this one is just the volumes per areas. Volumes per areas. It's just volume per areas. And as we have expanded as many as 500 thousands acre, and each acre needs 3 acre-feet per acre. So finally, we can actually determine the amount of water used. And so this one is the amount of water used. So just convert this amount into billion gallon per day. Okay, just convert this amount into the billion gallon per day. So this is the amount of water used per entire area. And here it's the conversion factor. This 1.12 million acre-feet per year is equivalent to 1 billion gallon. So basically, this is just the conversion factors again. Okay, this is just the conversion factor again. So don't be wonder about the units. It's nothing complicated, just the conversion factor. But the information that I have just make it bold and underlined, like 140 and also 3 acre-feet per acre. This is the amount of water that we study or we have taken from other references to estimate the amount of water used. It's not there here in the question. As an engineer, we have to study further to collect this information. So this is the second segment. Then another segment is the electricity generation. Electricity generation is a bit complicated. As I mentioned, according to the idea that I have just explained, you have to check what kind of the generating system they are going to use, and based on the system that they used, how many liters, how many gallons of water are required. So according to this idea, you can find out the amount of water as they are going to produce or generate 4,000 megawatt. So 4,000 megawatt. So how many liters of water is required? So we just find out the information. Here are some informations related to the equipment that they use to produce the water. Finally, they come up with the conclusion that this equipment required 50 gallons of water per kilowatt hours. Okay. They may mention about the efficiency. They may mention about the 1 kilowatt installed capacities would produce this kilowatt hours for electrical energy each day. According to this, we need 50 gallons per kilowatt hours. Finally, you can actually use this information to estimate the amount of water required for the stream electric cooling. Okay, so based on this one, we can find out the amount of water required in the future. So this is just the situation. Here you will find you have to look into some references to get the information. Otherwise, you cannot solve for this question. This is just like the situation. The question that the engineer would get from the community, for example, you are asked to design the water treatment plant. That is just a question. That is just a problem. So in that case, you have to study how many population in this community, and what will be the expected populations in the next 20 years, and then what will be the amount of water used, how many liters of water used in their daily life, and what about other activities involved in this country, in this community, like that. So these are the information that the engineers has to study, or they may have to collect some information from other references to tackle, to overcome these problems, or to find out the solutions. Okay, So it's just the example to show some idea about how we can estimate the water used. Okay, so according to this example, do you have any question?
จ้าครับแล้วไอ้140นี่คือมาอย่างไงนะครับที่ว่าเป็นแกลลอนนะตอนแรก
ก็อันนี้ไงก็คือหมายถึงว่ามาจาก reference อื่นนะฮะตัวที่ไฮไลท์ด้วยสีด้วยตัวหนาเนี่ยกับ underline เนี่ยนะฮะคือมาจาก reference อื่นนะฮะไม่ได้อยู่ในนี้นะฮะคือเป็นตัวเลขที่อาจจะคล้ายๆกับว่า assume ขึ้นมาแต่ว่า assume จากreference หรือว่าข้อมูลที่เป็นไปได้และก็น่าเชื่อถือจากแหล่งอื่นนะครับรวมทั้งไอตัว3นี้ด้วยนะฮะแล้วก็รวมทั้งไอตัวที่underline แล้วก็เป็นตัวหนาทั้งหมดนี้เลยนะครับอันนี้คือเป็นตัวอย่างวิธีการคิดเฉยๆนะครับอันไหนอีกนะฮะมาจากไหนผมก็จำไม่ได้แล้วเหมือนกันนะครับอันนี้Okay, so we have completed 3 examples. Now, another example, probably you can try it as a homework. Once we finish this chapter, there will be one big assignment containing several problems you can practice. So if we could finish it, this chapter today, I can distribute the assignments.
อาจารย์ครับผมมีคำถามนิดนึงครับจากข้อ3ครับเราตอบเป็น million liter per day แต่ว่าตอนที่เราดูในที่เป็นไฟล์ demand หน่วยมันเป็น gallon per minute ไม่ใช่เหรอครับอาจารย์
ถูกต้องแต่ว่าเราต้องเปลี่ยนเป็นไอตรงนี้มันคือ gallon per minute gallon per minute กับ gallon per day มันต่างกันยังไงอ่ะมันคือ flow เหมือนกันไม่ใช่เหรอมันแค่หน่วยคนละหน่วยกันเฉย
ๆแต่หน่วยใน example 3เราเป็น million liter per day ไม่ใช่เหรอครับอาจารย์ไม่ได้เป็นgallon
อันไหนนะฮะ example 3
ครับมันเป็น million liter per day
million liter
gallon ไหมครับ
per day อันนี้เดี๋ยวเช็คอีกทีนะเดี๋ยวเช็คอีกทีหนึ่งนะครับเพราะว่า F หน่วยมันเป็นแกลลอนใช่ไหมนะฮะไม่แน่ใจว่าตัวเลขไอ้ตัวนี้มันเขาเรียกว่าอะไรนะ multiply by 3.8 ไปแล้วหรือยังนะครับเดี๋ยวเช็คไอ้ตรงนี้อีกทีหนึ่งนะฮะ
อาจารย์ครับแล้วถ้าสมมติ
แต่ตอนที่คำนวณออกมาได้เนี่ยมันจะเป็น gallon per minute แต่ว่าถ้าเราจะเป็น million liter เนี่ยก็จะต้องคูณด้วย3.8 ก่อนถึงจะเป็น million liters per day นะครับ
คูณเข้าไปใช่ไหมครับไม่ได้หารใช่ไหมครับ
no 1 แกลลอนเนี่ย1 แกลลอนคือ 3.78 million 3.78 ลิตรนะฮะ1 แกลลอนคือ 3.8 ลิตรถ้าเราได้เป็นแกลลอนอยากจะแปลงเป็นลิตรเราก็ต้องคูณถูกไหมถ้าเรามีลิตรจะแปลงเป็นแกลลอนเราก็ต้องหารใช่ไหมฮะใช่ไหมยุคเจเนอเรชันของพวกเราไม่ค่อยได้ทำconvert unit conversion ใช่ไหมหลังๆมา
ใช่ครับ
ครับยังไงต่อ
อาจารย์ครับคือเราใช้น้ำไปทำอะไรกับไฟ
น้ำเนี่ยปกติเราผลิตขึ้นมาแล้วก็เก็บไว้เฉยๆแต่เมื่อไหร่ก็ตามที่มีเพลิงไหม้ไงเราก็จะเอาน้ำไอ้ตรงนั้นน่ะมาดับเพลิงนะฮะความหมายคือไฟ demand เนี่ยก็คือสำรองน้ำใช้เพื่อการดับเพลิงเพราะว่าถ้าเราไม่คิดถึงส่วนนี้เนี่ยนะเราจะไม่มีน้ำสำรองหากเกิดกรณีของเพลิงไหม้นะครับอันนี้คือ community หรือว่าอาคารทุกอาคารเนี่ยจะต้องมีไอตัวstorage ตรงนี้เพื่อที่จะspare ไว้สำหรับfire protection ถึงแม้ว่ามันจะไม่ได้ใช้ตลอดเวลาก็ตามแต่ว่ามันก็จะต้องมีcapacity ที่สามารถที่จะ supply ได้เกิด extreme case แบบนี้นะครับ
อ๋อโอเคครับงงตั้งนานครับอาจารย์
File demand เดี๋ยวนะผมดูเอกสารเดิมทีเนี่ยนะฮะyou will get after อันเนี้ยนะฮะมันจะได้4575 gallon per minute 4575 gallon per minute 4,574 มันจะได้4574นะฮะ4574นะครับไอ้ตรงนี้มันจะได้4574นะครับแล้วเราก็convert ให้เป็น million liter per day นะฮะมันจะได้ gallon per minute แล้วก็ convert เป็น million liter per day เปลี่ยน gallon เป็นลิตรคูณด้วย 3.78 แล้วก็เปลี่ยน minutes เป็น day นะฮะ minutes เป็น day นี่ทำยังไงอะจากนาทีเปลี่ยนเป็นวันนะฮะลองไปไล่ดูนะฮะนาทีเปลี่ยนเป็นวันสมมติว่าเปลี่ยนนาทีเปลี่ยนเป็นวันทำยังไงฮะหารด้วยอะไรหารด้วย60ใช่ไหมนาทีเปลี่ยนเป็นชั่วโมงก่อนแล้วจากชั่วโมงก็เปลี่ยนเป็นวันแล้วก็หารด้วย24ถูกไหมฮะ
คือหารด้วย60แล้วก็หารด้วย24ก็จะกลายเป็นวัน
ก็จะกลายเป็นวันจาก minutes เป็น day นะจาก minutes เป็น day
โอเคครับ
นะฮะ but you need to verify this again this is not equal to this one okay but this you will get 4,574 gallons per minute and after converting these gallons per minute to million liter per day you will get this one 24.9 reconvert these units because in the previous equations we have determined and already expressed in terms of milliliter per day. That is why we just converted into the same. As I mentioned, only the same units can be combined or can be subtracted. Different units cannot be combined. That is general rule. นะครับโอเคฮะtwo other example I expected you will do it as a homework. Okay. So if there's no other question, then we move to the next topic. In this topics, the population forecasting. Population forecasting, you may realize, according to this 3-4 example, you may realize the information about the population number is important because we mostly have the per capita use, but we don't have the number of the populations. So if we want to predict the number of the populations in the future, what we can do, this is the procedure we're going to move into. For the population forecasting, the procedure that we are going to talk about in this chapter is only used for estimate the population for designing the treatment facilities, or maybe for the designing some infrastructures in the community. We don't use this method to predict the real populations in the future, because predictions of the real of the populations in the future, there are numerous factors involved. Okay, we cannot do like what will be the populations of the Thailands in 2030. We cannot apply this method, but we use this one just to just for design the treatment facilities, or sometimes designing other public infrastructures. So okay, for the population forecasting, populations, of course, we know that it really affects the water use, the age, the levels of the education, the social background, fields of employment, religious belief. Some, religious, they pray several times a day before praying. They have to wash their hand, wash their food before praying. They may consume more water based on the compared to other religions, but it's not much anywhere. But anyway, there's some way of a different way of using water. Fields of employment, some occupation may require more water. Some occupations require less water. If they are well educated, they are really aware of health, they may use a lot of water for the hygienic purposes. Social backgrounds also, if they are like persons who are working in the hospital, they're really concerned about the infection, so they have to wash their hands, they have to take a shower very often.เหมือนเสียงประทัดนะฮะไม่ได้มาจากบ้านผมใช่ไหมนะฮะบ้านใครจุดประทัดหรือเปล่าในนี้นะฮะ Okay, other important factors: geographic distribution, growth rate, natural resources, energy requirement, urban infrastructure. So these are the factors which also related to the population and link it to the water uses in the community. For the population forecasting, especially forecasting for the operations and designs of the water treatment facility, we normally predict for the next 10 years. 10 to 20 years is considered as the short term, but for the long terms, it means that we predict it for like 50 years or even more. There are a number of methods that we can use to predict the populations in the future. But anyway, before predictions, we need to collect the informations, the current populations and the past 5 years or probably 10 years, because we need to see the growing trend. And here is the source of the informations. You may get this information from the Ministry of Interior or the municipality, local municipality, planning commission, bureaus of vital statistics, and so on. Mostly we use the trend-based methods. So what are the trend-based methods? The population may increase like this. There's a sharp increase in the beginnings of the periods. These types of increase is called the geometric increase. You see the slope, it's increasing. So if you just consider only this part, the slope is increasing. Okay, but if it increases like this in between point A and point B, you see this is a constant increase. The slopes is constant. The slopes of the curve is constant. Okay, so this one is called the arithmetic increase. This is arithmetic increase. Okay, this is more or less like a straight line. And the last growing trend, so it's increased, but increased with the decreasing rate. Increase with the decreasing rate. You see the slope is the decreasing. Okay, the slopes is decreasing. The slopes of the line is decreasing. So there are mainly three types of the trend of growing. But anyway, for the last growing trend, so it finally reached the maximum value, or generally we call the saturated populations. So populations will not increase beyond this this line. Okay, this is the maximum for some community. It will never goes beyond this line under the present conditions. Actually, there are more. The trends are more. There are more than three trends of the populations, but not the growth, but declining. Many cities in Thailand experienced population decreasing. Okay, but anyway, decreasing is not a problem because the infrastructures are already there, so we have no worry about the future. Anyway, it will be sufficient for the current populations. But here we are considering only in case of the people increase in the future. Okay, we are not talking about the declining of the populations. Okay, so there are basically three types of growing trend: geometric increase, arithmetic increase, or constant percentage growth rate. And then the last one, decreasing rate of increase. It's still increasing, but with the decreasing rate. Basically three types of the estimation. So these are the short-term estimation. So it's good enough for providing the information about the populations in the near future, but it may not give the exact number. But as I mentioned, estimation according to this method, we only use for designing and operating the water treatment plant. We are not aiming to apply this method to find what exactly the populations in the country. Okay. There may be some other types of the short-term estimations, like a graphical extension, but we rarely use this one. Okay, let's look into each method. Arithmetical increase or arithmetical progression. Sometimes we call it constant increased. As you can see, this is the straight line. So it just increases with the constant growth rate. This line in between point A and point B. So if you establish the mathematical expression, you will get something like this. dy by dt is constant. The slope is constant. So it's equal to a constant. So these constants we call uniform growth rate constants. Y is the populations and T is the time. Okay. So according to this mathematical expression, I assume that we are all now expert in mathematics, especially the calculus. So if you're good in calculus, this will be very simple for you. So just try to find out the answer or the solutions of this equation. So if you want to find out the solutions of this equation, so you just move dt into k and then integrate. Finally, what you would get some equations like a straight line describing a straight line characteristic. Y is equal to y0 plus kt. Y is equal to mx plus c. So it's a format of the straight line. Then what is k? K is the difference between the populations in year 1 and year 2. divided by times difference. Okay, so we'll see again how we can apply this arithmetic progression to predict the populations in future. For the geometric increase, or a constant percentage growth rate. For a constant percentage growth rate, the slope is increasing. The slope is increasing. So we can actually write the mathematical expression divided by dt is equal to ky. Y is the populations. So this one is different from this one. This is a constant value, but this one is a constant into y, or the population. So here, if you want to find out the solution, so you have to move dt up and move y down to another side. Dy divided by y is equal to k dt. So in this case, integrations of dy by y, you will get logarithms functions, natural logarithms functions. You will get something like this. The populations of the populations in year y, it's equal to the populations in the present year plus k, a constant, multiplied by the times different. So that is the second method. Then the last one, decreasing rate of increased. For the decreasing rate of increase, as I mentioned, the population nearly reached the saturating point, limiting value. Then the mathematical expression becomes like this. So dy by dt it's equal to the constant into this difference sets is the saturation of limiting value minus y. See, y is governed with the minus. It means that the slope is decreasing. Again, we do the same procedure, and then finally we come up with this relationship. Population in the future is equal to the populations in the present years plus saturated populations minus the populations in the present years into 1 minus e to the power of k t. T is the duration period. So this is the relationships we use to find out the number of the population based on the decreasing rate of increased. The last one is a little bit complicated logistic curve method. The population in the future is equal to the saturated populations divided by 1 plus e to the power of a plus b times periods. Then you can find out the terms, the saturation populations, values of A, values of B, and then once you know the saturation populations at A and B, you can find the populations in the future Y. Okay, this one is the logistic curve method. Even the simplest method that everyone could actually used for the predictions, the components method. What is the components methods? Components methods is the populations in the futures can be simply calculated from this definitions. The populations at the end of the time interval is equal to the populations at the beginning of the time plus a birth minus a death and then plus or minus migration. So this is very simple, but we rarely use this one. Mostly we use the trend-based method, these three methods to estimate the populations. But anyway, sometimes you can use it. Sometimes we have no idea about the number of the populations, but we know that this particular area, so what types of the areas will be, what activity will be doing in the future, or what kind of facilities will be allocated in the futures in this area. For example, if they want to make it a residential single family units in this area, we can estimate the number of the population based on these types of the areas, the apartment or the commercial areas, industrial areas. So once we know the land use pattern, then we can predict the number of the populations in based on the area type. So we don't have to apply a trend-based method. Alternatively, we can use this method to estimate the number of persons. Okay, then just come to the example for the population's prediction. For the population prediction, okay, a mid-sized city record a populations of 113,000 and 129,000 in April 1980 and April 1990 census. Estimate the populations in January 1999 by comparing three methods. So let's begin with the first method, arithmetic method. According to the arithmetic methods, it's basically the straight line. Y is equal to y2 and then k into the times interval. First, we begin with the constants determination. So as we have two sets of data, the first set of data it's obtained from April 1980, and then the second set is obtained from April 1990. 1990, the population increased from 113,229,000 during 10 years, during the periods of 10 years. So we can find out the constants. And once we know the constants, and then we want to apply these arithmetic methods equations to determine the populations in January in 1999. 1999, supposed the current year is 1990. So this is 1990, and this one is the constants. But what about the times interval? From April 1990 to January 1999, 1999, January, not April. So it's not exactly 9 years, but it's 8 years something, okay? 8 years and 9 months. From April to January, it's 9 months. So the times interval, considering from April 1990 to January 1999. So the times, it's 8.75 years, not 9 years, okay? So it's 8 years and 9 months. So then we just substitute this value into this equation. Then finally we find the populations in January 1999 is 143,000 population. So this is the value that we have obtained from the arithmetic method. In fact, we don't know the growth, population growth in this community will behave like a arithmetic methods or geometric increase or declining rate of increase. We don't know. But the idea is that we determine these three methods, which methods to give the maximum number. We take that one. Actually, the maximum number is the most conservative value. So we only take the most conservative values to be used for the water treatment plant designs and for other purposes related to the designs and operations of the urban infrastructure. Our second method, so it's the same thing, just find out the constants, then substitute these constants into the equation. The period is 8.75 years, not 9 years. We finally get population calculated by this method. We have got 144,800 population. Then again, just so for the last method, declining growth method. For the declining growth method, you really need the population saturated population's value. For the decreasing rate of increase, you need the limiting value here. Okay, so as you need the saturated population, so you have to pick up one value for the saturated population. So that may be obtained by assuming, you may assume the value which may be close to the population that you predict. For example, you may choose why we choose 200,000, because in the previous method, so we have got like a 140 something. Second method, we also get 140 something. So you can pick up around 180,000 or 200,000 as the you can use this as the saturated population. So once you assume, I mean 200 is possible, it actually makes sense. But if you pick like a 500,000, so it's far beyond the value we generally get. So in this case, it may not be reasonable. The reasonable value should be around not much higher than the value we have obtained from other method. So let's say like a 200. So if we use 200, then we apply it again in this equation. We begin with the determinations of the constants. So once we know the constant, substitute all this value into the equation, and then we get the populations in a year. In January 1999. So here you will find these three methods to give different population number. So if you are asked to determine the size water treatment plant. So which number you will pick up? Because you need one of these number to and then multiply it by the water consumption. You will get the capacity of the treatment plant. So which number you will pick up? Which one? So you need the most conservative number. So the most conservative number means which methods give the highest population number. We take that one. So in here are the methods that give the maximum number. It's from the constant percentage method, so that the population that we pick up from the prediction is 144,800 population. So we take this one to for the design and operations of the water and wastewater treatment plant. If you pick this one, what will happen? Some number will get lost. Okay, you get less amount, you get less quantity. The larger is better, but the largest is not always the best option for the designing the engineering infrastructure. Okay, so these are the values that we obtained from these three methods.
จ้าครับ
ครับ
สเต็ป 3อาจารย์ลืมลบหรือเปล่าข้างหน้าสัญลักษณ์ลบอ่ะ
อันไหนเอ่ย
KD ครับ KD เท่ากับลบ1ส่วน T2 ลบ T1 อาจารย์ลืมใส่ลบป่ะครับในกรอบอ่ะสเต็ป 3อ่ะ
กรอบอันนี้เหรอ
ไม่ครับอันแรก
boxed อันนี้เหรอฮะ
ใช่ครับ
just go back to this again
ครับแต่ว่าตอนที่อาจารย์พูดตัวเลขลงอาจารย์ไม่ได้ใส่ลบมันค่าจะผิดหรือเปล่า
ใช่ต้องใส่ฮะ
ครับแล้วมีคำถามหนึ่งคือเราจำเป็นต้องทำทั้ง3สมการเลยใช่ไหมครับเพื่อที่จะรู้ว่า
คือ
มากที่สุด
เราไม่รู้ว่าวิธีไหนมันจะให้ตัวเลขเยอะสุดเราไม่รู้คืออันนี้พูดถึงเนเจอร์ของการเพิ่มขึ้นของประชากรของเมืองใดๆก็ตามเราไม่รู้ว่ามันจะเพิ่มขึ้นเป็นแบบเพิ่มขึ้นโดยที่ความชันเพิ่มขึ้นที่เราเรียกว่า geometric increase หรือมันจะเพิ่มขึ้นเป็นแบบ constant หรือมันจะเพิ่มขึ้นเป็นแบบ decreasing rate of increase อันนี้เราไม่รู้ในอนาคตแต่ว่าเราอาจจะประมาณการได้ถ้าเรามีข้อมูลในอดีตย้อนหลังกลับไปแต่ว่ามันก็ไม่ใช่เทรนในอนาคตอยู่ดีนะฮะเพราะฉะนั้นเนี่ยนะฮะเราก็จะ try นะฮะประมาณ3 method ตรงนี้แหละเป็น most common tree method ตรงนี้แหละนะฮะเพื่อที่จะดูว่าอันไหนyield maximum numbers และเราก็จะใช้ไอ้ตัว maximum number ไอ้ตรงนั้นนะเอาไปคิดนะเพราะว่าเราถือว่าไอ้ตัวไหนที่ให้ตัวเลขมากที่สุดตัวนั้นจะเป็น the most conservative number นะฮะครับเพราะว่าเราไม่รู้ว่ามันเพิ่มขึ้นแบบไหนเราก็เลยจำเป็นต้อง try 3 วิธีครับหรือจริงๆอาจจะ more than 3 methods ก็ได้นะ but at least 3 is reasonable นะครับอย่างอื่นมีไหมฮะ
ไม่มีครับ
อาจารย์ไอ้ set value ครับตรง declining goal method ครับเราเอาซูเป็นเลขอะไรอย่างอื่นได้ไหมนอกจาก 200,000 ครับ
ได้แต่ว่ามันไม่ควรจะหนีจาก 140,000 มากเท่าไหร่นะฮะเลขอื่นก็ได้นะไม่จำเป็นมันไม่ควรจะหนีจาก 140,000 มากนักคือจริงๆแล้ววิธีนี้เนี่ยมันจะเป็นวิธีที่มันมีความไม่แน่นอน2ชั้นพวกนี้ก็มีความไม่แน่นอนในระดับหนึ่งแต่ว่าไอ้ตัวนี้มันจะมีความไม่แน่นอน2ชั้นมันขึ้นอยู่กับไอ้ตัว saturation population แล้วจริงๆแล้วพวกนี้เนี่ยนะครับถ้าจะให้ดีเนี่ยนะครับมันก็ต้องมีแบบอย่างเงี้ยนะฮะอันนี้คือthe next examples are showing the information about the populations in various year. So if you plot this information, for example, from year 75 to year 79, you will see some trend. And if you already have the train, probably in the next 10 years, you can choose the right method to estimate the population. You may ignore the third method in this case. But based on this information, so we have no choice. So we have to anyway, we have to assume this number. But you shouldn't far away from the number that we have already tried. We are already great. Generally, we get we already have like a 144. You shouldn't try 500, or you shouldn't try 1 million. That doesn't make sense นะครับ
อาจารย์ครับสมมุติเราใช้เป็น150,000ได้เปล่า
150,000ถ้าเป็น150,000เนี่ยนะฮะมันใกล้เคียงกับ140,000มากเกินไปคือถ้าเราคิดว่ามันเป็น150,000เนี่ยแล้วคำถามมันจะย้อนกลับไปที่2เมธอดแรกนะฮะคำถามมันจะย้อนกลับไปที่2เมธอดแรกนะครับว่าเอ๊ะมันใกล้150,000แล้วนี่นะฮะทำไมเราถึงไม่เรียกได้ไงนะเลือกวิธีนี้วิธีเดียวไปเลยถ้าอย่างนั้นนะครับเพราะมันก็ควรจะอยู่ในเลเวลที่ห่างออกไปนิดนึงแต่ว่าไม่ถึงกับใกล้กับไอตัวที่เราจะได้มาสักเท่าไหร่นะครับคือยังไงก็ตามเนี่ยนะพวกนี้มันคือ prediction เพื่อเอาไปทำอะไรเอาไปประมาณการนะฮะคือเวลาเราทำงานทางด้านวิศวกรรมอะไรใดๆก็ตามเนี่ยนะฮะเราจำเป็นที่จะต้องมีที่มาที่ไปของข้อมูลนะครับซึ่งนะฮะความน่าเชื่อถือของผลนะฮะมันก็จะมาจากข้อมูลที่เราอ้างอิงหรือว่าหามาถึงฉะนั้นเนี่ยนะฮะไอ้ตรงนี้ก็เหมือนกันนะครับเวลาเราจะดูนะฮะตัวแนวโน้มเนี่ยจริงๆวิธีเหล่านี้เนี่ยนะฮะเป็นวิธีที่ใช้ในกรณีที่เราไม่เคยมีข้อมูลมาก่อนแต่ว่าถ้าเรามีข้อมูลมาอยู่แล้วในระดับหนึ่งนะฮะเราจะใช้ไอ้ตรงนี้แหละนะฮะเป็นตัวหลักเผลอๆเรามีข้อมูลอย่างนี้มาสมมุติว่าเรามีข้อมูลย้อนหลังนะฮะแล้วเรามีข้อมูลย้อนหลังเนี่ยนะฮะย้อนกลับไปสัก10 ปีแล้วเราต้องการที่จะ predict อีก10 ปีข้างหน้านั่นแปลว่าเรามีข้อมูลมาแล้วครึ่งทางเราต้องการ predict อีกครึ่งทางเผลอๆนะฮะดูจากข้อมูล10 ปีย้อนหลัง10 ปีถัดไปเนี่ยเราอาจจะเลือกแค่วิธีเดียวก็ได้ไม่จำเป็นต้อง try 3 วิธีนะฮะที่เรา try 3 วิธีเนี่ยก็เพราะว่าเราไม่มีตัวเลขที่มันแน่ชัดในเรื่องของเทรนเราก็เลยเลือกหลายวิธีนะฮะแล้วก็ดูว่าตัวไหนนะฮะให้ conservative value นะฮะเราก็พิกัดตัวนั้นนะครับในกรณีนี้นะฮะ
อาจารย์ครับแต่เราก็ไม่รู้อยู่ดีนี่ครับว่าเลขมันจะใกล้150,000หรือเปล่า
เราไม่รู้อันนี้เราไม่รู้ฮะถ้า based on ไอตัว information ที่อยู่เท่านี้นะครับเพราะฉะนั้นเนี่ยนะฮะไอตัว method ที่3เนี่ยนะก็ยังถือว่ามีเขาเรียกอะไร reliability ที่มันไม่ใกล้มันจะอีกสเต็ปหนึ่งห่างออกจากmethod ที่1กับ method ที่2นะครับแต่อันนี้ก็คือก็ลองเอามานะฮะดูกันไว้มันจะมีวิธีการในการคิดยังไงนะฮะถ้าถามว่า saturated population เนี่ยในความเป็นจริงนะฮะเราจะรู้ไหม saturated population เนี่ยถ้าตราบใดที่ community ไหนเนี่ยไม่เกิด population decline เนี่ยนะฮะเราก็จะยังไม่เห็นจุดนั้นนะฮะแต่เมื่อไหร่ก็ตามถ้าเมืองไหนที่มีdeclining เนี่ยนะฮะเราก็จะรู้แล้วแหละว่า saturation population มันอยู่ที่ตรงไหนนะฮะคือหมายความว่า saturation population เนี่ยก็คือจำนวนประชากรอิ่มตัวสูงสุดนะฮะคือเลยจุดนี้แล้วเนี่ยมันจะเป็นยังไงฮะมันก็จะลดลงเมืองไหนก็ตามที่มี information ที่เป็นลดลงปุ๊บเนี่ยเราก็จะรู้ไอ้ตรงนี้แต่ถ้าเมืองไหนก็ตามที่มันยังอยู่ในสภาพขาขึ้นไปเรื่อยๆไอ้ตัวนี้ก็ต้องเป็นไอ้อะไรเป็น assumption นะฮะอันนี้ก็เป็นตัวอย่างนะฮะทีนี้นะฮะใน example นี้เนี่ยนะฮะมันจะมีข้อมูลอยู่หลากหลายข้อมูลนะฮะอันนี้จะฝากไปคิดเป็น assignments นะฮะว่าใช้วิธีการต่างๆเหล่านี้เนี่ยนะครับตัวเลขนะฮะเราจะใช้ตัวเลขไหนนะฮะเราจะใช้วิธีการไหนนะฮะเดี๋ยวเราลองมาดูกันนะฮะในครั้งถัดไปนะฮะ มีคำถามอะไรเพิ่มเติมอีกนะครับ ก่อนที่จะไปหัวข้อสุดท้ายของบทนี้คำตอบอันที่ 4เนี่ยคุณคิดยังไงใน example 4เนี่ยคิดยังไงกับคำถามอย่างเงี้ยปกติแล้ว arithmetical progression เนี่ยเราต้องใช้ข้อมูลเท่าไหร่นะฮะ2 คู่ใช่ไหมนะฮะเราจะใช้คู่ไหนฮะ arithmetical progression เนี่ยหรือ geometrical progression geometric progression decreasing rate of increase เนี่ยนะฮะเราจะใช้คู่ไหนที่ผ่านมาเราใช้ข้อมูลเป็นคู่หมดเลยเราจะใช้คู่ไหนมันมีตั้งหลายคู่
ตัวแรกกับตัวสุดท้ายไม่ได้หรอครับ
ใช้ตัวแรกกับตัวสุดท้ายมันก็ได้ตัวเลขหนึ่งถูกไหมฮะ
ครับ
ถ้าใช้ตัวแรกกับตัว1977กับ1979คุณก็ได้ตัวเลขอีกตัวเลขหนึ่งนะฮะอันนี้เดี๋ยวฝากไปคิดแล้วเดี๋ยวลองเอามาดูกันอีกทีนะฮะหรือจะต้องใช้ทุกคู่เลยนะฮะมาคิดแล้วก็โอ้โหไม่งั้นเราจะได้คำตอบเยอะมากนะฮะโอเคอันนี้เดี๋ยวลองฝากไปคิดก่อนนะครับอันเนี้ยฮะว่าไงฮะ
ผมว่าเอา1977กับ1979อาจารย์เพราะว่า76กับ77เลขมันใกล้กัน78 79เลขใกล้กันได้ไหมครับ
ถ้าเป็นผมจะเอาข้อมูลพวกนี้ไปพลอตก่อนนะฮะถ้าเป็นผมนะผมจะเอาข้อมูลพวกนี้ไปพลอตก่อนแล้วผมค่อยเลือกว่าเราจะเอาคู่ไหนนะครับนะฮะเผลอๆผมอาจจะใช้75กับ79ก็ได้นะฮะไม่รู้ลองดูนะฮะแล้วถามว่าถ้าเราเห็นเทรนด์จากการพลอตเนี่ยนะฮะมันอาจจะบอกได้ว่ามันเป็นแบบไหนคือถ้ามันเป็นอย่างเงี้ยมันก็เป็น constant ไม่ใช่เป็นอะไรนะเป็นแบบแรกgeometric increase ถ้ามันเป็นแบบนี้มันก็เป็นarithmetic แล้วถ้าเกิดว่าเอาไปพลอตแล้วมันเป็นอย่างเงี้ยล่ะนะฮะเหมือนกับตัว S ทำไงนะครับอันนี้ก็อาจจะต้องน้ำหนักของทั้ง3 method มันก็อาจจะใกล้เคียงกันเพราะฉะนั้นก็จะอยู่ที่เรื่องของการเลือกอีกแหละว่าจะเป็นข้อมูลคู่ไหนนะฮะอันนี้ลองไปคิดดูก่อนนะฮะฝากลองไปคิดดูก่อนนะฮะโอเคnow how many question I left it for you to do it as a assignment how many question 3แล้วใช่ไหม one two these two question are really simple but this one is but the third one is it's a little bit tricky so แต่คำถามข้อนี้เป็นคำถามที่ simple มากนะฮะเพียงแต่ว่าวิธีการทำเท่านั้นเองนะฮะอาจจะต้องคิดนิดหน่อยนะฮะคือไม่มีวิธีการไหนผิดถูกเพราะว่ายังไงก็ตามมันคือ estimation นะฮะแต่ว่า estimation แบบไหนจะ make sense มากที่สุดไอ้ตรงเนี้ยนะฮะจะเดี๋ยวเราลองมาดูกันนะฮะถ้าเราลองดูอันนี้เราพูดกันโดยทั่วไปนะฮะวิชาชั้นปีที่3ปีที่4เนี่ยเอาตั้งแต่ reinforced concrete มาเลยแล้วกันนะฮะที่เราเรียนเนี่ย steel timber design เนี่ยนะฮะส่วนใหญ่แล้วคำตอบมันจะไม่ได้มีคำตอบเดียวนะแต่ว่าคำตอบไหนจะเป็น the best ภายใต้ condition เนี่ยนะฮะเราพูดถึงอย่างนั้นมากกว่าบางคำตอบเนี่ยเป็นคำตอบที่ถูกแต่อาจจะไม่ใช่ the best อาจจะเป็น second best ก็ได้นะครับเพราะในหลักในวิชาในชั้นสูงเนี่ยนะครับจะเป็นลักษณะคำตอบเป็นแบบนั้นนะครับokay so we are nearly finished this chapter so let us finish within 10 minutes the last topic is the wastewater generations so I have mentioned about the wastewater generations several times one this aspect I have already talked about it in the last part of the first chapter if you still remember but anyway what I'd like to add from the chapter 1 is for the wastewater generation. So it's really it has very close link to the water use pattern. As I mentioned, about 60 to 80% of water become a wastewater. And in terms of the water use pattern, as I told you, if we use like this, if the water use pattern is just like this, then what about the wastewater generation? So wastewater generation is, so as it is just only 60 to 80% of the water use. So wastewater may be like only 60-80%, so not as high as the water use. And the other thing is you will see the time lag. So the peaks occur here, and then for the wastewater, the peaks will occur like a few hours after the peak of the water used. Peak of the wastewater maybe like 30 minutes or less than 1 hour occur after the peak of the water use. So wastewater generations and water use pattern are basically the same, but just the time lag, and the hike of peak may be smaller than the peak of the water use or water demand. So this is the difference between the water use and wastewater generation. Talking about the peak factor, the peak factor are based on the Goodrich formula. So if the period is 1 day, the peak is 1.8 or 180%. That is the typical. But there are some other conditions that could actually influence the peak factor. Remember that the peak factor is the ratio between the Q peak and the Q average. So if you take the Q peak divided by the Q average, the value we have got, we generally call the peak factor. Peak factors, okay? So the peak factor is the ratios of peak to the average flow. So peak can be peak factors can be used to explain water use variations and also the wastewater generations. For the wastewater generations, the peak factors could be as high as the 3. The Q peak is 3 times greater than the average flows for smaller populations, or for the like 10,000 populations. But if the population is large, like 1.1 million, the peak factors could actually reduce to 1.5 only. So what we have learned from this information, the larger populations will be the lower peaking factor. So this is the fact that you can actually compare to just one single house. What's wrong with my applications? So it, and these two doesn't move. These two objects don't move together with the other object. Okay. What will happen to water use in your house? Just in your house. So your house, there may be like 4 or 5 persons. Early morning, 0 water usage, but then 4 or 5 people wake up. What happened? start using a water again, and then finish. So during the daytimes, nobody's staying at home, so zero water usage. And again, 4 or 5 people come back and use that water. So there is a peak here and there's peak here. So what will happen to the average flows? What will happen to the average flows in this case? The average flows, you have to take each individual hours combined and then divided by 24. And there are so many hours give a zero usage. So the average flow is just this one, very small average flow. This is Q average. This one is Q peak. So if you are taking Q average, Q peak divided by Q average, what will happen? The peaking factor would be very high. But in your house, if there is an elderly, your grandmother, grandfather, they don't go for work, they have already retired, they wake up very early, so they use some water, and then you and your parents wake up, and of course you had gone to the universities, and your parents had gone for work, but still your grandparents or the family's member who stay at home, who live there, still use water, even a small amount. So what will be the average flow rates? So the average flow rates will be a little bit greater, and this one is the peak factors, because your grandfather and your grandmother, they don't have to go for work, so that they don't use that water at this time. They may take a shower at 10 o'clock, or they may take a shower at 6 o'clock. So what will happen to the Q average? So Q average will be a little higher as compared to these conditions. So if you are taking a Q peak divided by Q average, so you get the peak factor. It's high, but not that high as compared with the family, the families that they left home during the daytimes. So what we have learned from these two comparisons. So more member, the peaking factors is smaller than small number of families member. So the same as I have mentioned in this slide, the larger populations will be the lower peaking factor. Okay. Estimations of the wastewater flows, we can say that 60 to 80% of the water use become wastewater. So it's reduces according to the amount of water used. This one is the statistical record showing various cities in the US showing the amount of wastewater flows. So the amount of wastewater flows expressed in terms of gallons per capita per day or liters per capita per day. This textbook, Reynolds and Richard, I think the names of the textbook, the titles of textbooks is Unit Operations and Processes in Environmental Engineering something. This textbook, it's they used like both the unit. The examples also showing 2 units, both SI and US customer unit. So here is the wastewater generation rate expressed in terms of liters per capita per day. But this one is the wastewater flow rate expressed in terms of gallons per capita per day. So as I told you, 1 gallon is equal to 3.8 liters. And the last column is the percentage of the water demand. generally speaking, it's 60 to 80% of water becomes a wastewater. But here is the statistical record. Some cities, for example, Baltimore, the percentage of the water demands is only 63. But in some cities, 100%. So they have very good sewage collection system. Some towns, you know, in US, they don't allow the inhabitants to watch their own car in their house. It's actually violate the law if they do it. Okay, penalty will be imposed to those who watch their cars in their own house. In some cities, they even launch the municipality regulation. What types of plants the local inhabitants can grow. Some types of plants, some vegetables are prohibited because it consumes lots of water. See, this is a kind of regulation. Why? Because they are facing the water shortage. That is why they don't want the people used a water with various purposes. They don't want to lost any water, tapped water, even though it becomes a wastewater. They still want to reuse that wastewater, treat it and reuse it again. That is why some city you could see like they have very good sewage collection system. The percentage of water demands is near 100. So whatever the water that they use, it becomes the wastewater. It's 100% become a wastewater. They can actually collect everything. But anyway, the average values, some cities they are doing very good, but some cities they have very poor connections, like at Los Angeles, only 46%. I don't know about Bangkok, how many percent of waste becomes of water becomes a wastewater. I'm sure that it's less than 40%. Anyway, anyway, it's returned to the nature, but here we are talking about the wastewater that can be collected. So the average is 76%. So we can say like in between 60 to 80% of water become wastewater. So this one is the daily variations in wastewater flows. As I told you, there's a peak, there's a minimum flows, and there's an average. So these figures vary from one to another. Just few more slides. This one and this one, I think we have talked about. Okay, maybe I just finish it up to here. Probably we discussed a few more slides again next week because now it's already 12:30 and 1:30. We need to meet again in the lab session. Okay, we leave it. We'll discuss further next week for this 2 or 3 slides before finishing this chapter. But anyway, maybe today, if I will not forget, I will distribute the assignments regarding to the water use and water demand. There are some more questions. You already have 3 questions. So I distributed where the assignment system of the MS team. So please wait. And the expected date for the submission could be next week, sometimes next week. By the way, based on this today's lectures, do you have any question? มีคำถามไหมครับ Otherwise